Let's do another angular kinematics problem. We're looking here for the angular speed of the Earth, first as it spins on its axis and then as it revolves around the sun. And in the previous video, we just went through an equation that is going to help us often find the angular speed of something. The average angular speed is the angular displacement divided by time. And as long as the angular acceleration is constant, that could also be found by taking 1/2 times the quantity omega f plus omega I. And any two of these three bits of this equation could maybe help us calculate different quantities. So we want to find the angular speed of the Earth as it spins on its axis. So how do we do that? To find that, we need an angular displacement and a time that is applicable to that angular displacement. Often with things that are spinning, it's a good idea to say, well, the angular displacement is 2 pi radians. In other words, the thing goes one time around. And for the Earth spinning on its axis, how long does it take to go one time around? I'm hoping that you know that already, but if you want to say it as 1 day, that's fine. If you want to say it as 24 hours, that's fine. I'm going to use it as 24 hours. Now, we're going to want our angular speed in radians per second, so we're going to have to do a little converting, but essentially, we've got the pieces of the puzzle that we need. Let's see what we can do here. The average angular speed is the angular displacement divided by time. So that's 2 pi radians every 24 hours. Now, there's nothing wrong with that answer. You would get an answer in radians per hour, but I'm going to want to report it as radians per second. And so we're going to have to convert between hours and seconds. And what do we know? There are any number of ways you could do this. I'll show it the long way. 1 hour is 60 minutes. I orient the conversion factor like that so that the hour units cancel. And 1 minute is 60 seconds. The minute unit cancels. And if you type that into your calculator, again, you would use a number for pi, like 3.14. We're going to want a decimal here. We don't have any numbers that are given, so we really don't know to how many significant figures to round this. So it really doesn't matter. But I'm going to go ahead and round it to 2 significant figures. And when I typed it in, I got 7.3 times 10 to the negative fifth. And what are the units for angular speed? Radians per second, and that is shown right here in our work. We have radians in the numerator and seconds in the denominator. That represents a rate at which the Earth is rotating. The Earth also goes around the sun. And the only difference between the calculation we're about to make and the one we just did is the time. Because when the Earth revolves around the sun, let's say it goes around once, therefore the angular displacement is 2 pi radians, but the time is definitely not 24 hours. The time is more like 1 year. If you want to write 1 year here, you're welcome to do that, but I'm going to go ahead and write 365 days, and one more time, I'm going to convert this into radians per second. The average angular speed is the angular displacement divided by time. That's 2 pi radians in 365 days. But I'm going to want my answer in radians per second, so let's do a little converting here. 1 day is 24 hours. The day units cancel, like that. That would give us an answer in radians per hour, but I don't want radians per hour, I want radians per second. So I'm going to go 1 hour. And here's a little shortcut. Some of you might know this. but this will save me a conversion factor from what I did above. Above, I converted hours to minutes and minutes to seconds, and if we're clever, we might realize that, you know what, 1 hour is 60 times 60 seconds, so it's 3,600 seconds. The hour units cancel. This is going to give us a very tiny number to two significant figures, 2.0 times 10 to the negative 7th radians per second. As the Earth goes around the sun, the angular displacement changes by that many radians every second. You might remember when we were doing linear kinematics previously in this course, there were 4 equations that we could use if the acceleration was constant. And here they are, right here. This one we called the no-time equation, and then there were 3 others. Just like there is a correspondence with the angular velocity equation. In other words, there's our linear velocity equation, and there's its corresponding angular velocity equation. We did that a couple of videos ago. Just like there is a correspondence between linear acceleration equation, there's a matching angular acceleration equation. In the same vein, there was a no-time equation in linear kinematics. There's a no-time equation in angular kinematics. And finally, just like there was an equation that looked like that for linear kinematics, it exactly matches. The only difference is that the quantities up above are all angular quantities, and they're in radians, and radians per second, and radians per second squared. Then there's one equation that we're going to be introduced to. We met this in a previous video, and that connects angular quantities, which I'm putting a dot under right now, and linear quantities. That was the arc length is equal to r times the angular displacement. So there's one extra equation that we're going to be using in angular kinematics at this time, but the 4 that you are very familiar with, hopefully, have an exact match with angular kinematics. And lastly, for this video, the sign convention for angular displacement, angular velocity, and angular acceleration is that counterclockwise is positive and clockwise is negative. Clockwise is that way. It's not super important for most of our problems. We really don't need to worry about it